Okay. So far during chapter 2, I've been talking about error analysis in a general sense, dealing with average discretization error, data error. But in this next section, I'm going to focus on just one form of error, a particularly important one, and one that really highlights the significant difference between using analytical methods for solving mathematical problems and numerical methods. Because when you're solving problems analytically, you do not have to worry about the computer arithmetic and the error that it can introduce. But it's a significant issue for numerical methods, and failure to take this into account can sometimes lead to disastrous results. So this is where the class gets a little bit more computer sciencey than mathematical. We're going to look at how numbers are represented by a computer and the ramifications of that. The system that is used to represent numbers on most computers is a floating point representation. And a helpful informal description of a floating point number system would be it's like scientific notation that you're all familiar with from many different science classes, but working in binary. So computers have always used numbers in base 2, I got a notification about difficulty watching the class. Okay, I'll find out. I'll just have to get more information about that, so what goes wrong. So if anyone is watching this later, you're having difficulty, if you want to join the meeting and you're having trouble doing so, I need details, like is there a particular error message, preferably screenshots, anything like that, so to try to diagnose it. I may have to talk to people in the Office of Online Learning, see what's going on in that situation. Okay, now it's worth noting that I'd heard about computers developed in Russia a long time ago that actually used base 3. In base 2, binary makes sense because 0 corresponds to off and 1 corresponds to on. So I'm not sure what how base 3 would work in an electrical sense. I haven't taken time to look that up, but hopefully base 3 once upon a time was used. So it's interesting. Is it like off, on, and kind of on? So I don't know. Okay, so a real number that we want to represent is broken down into a few pieces of interest here. So we have the sign plus or minus, and then we have the base that you're using, beta. So on computers, the base beta would be equal to 2, and we're accustomed to base 10. That's raised to some exponent that conveys the magnitude of a number. And then we have here little m, that is the mantissa, so that consists of all of these significant digits. You think in terms of the significant digits from scientific notation, and that's this part of the number right here. So the idea is to, when you have a real number, to break it down into these parts to understand how it is stored internally. Okay. Now, as an example, I'm going to use x equal to 117. So I'd like to represent that in binary, but first, to contrast, we'll take a closer look at how it's represented in decimal if you were to use scientific notation. So in decimal, you could think of 117 as positive 1.17 times 10 squared. So 1.7 is the mantissa in this case. The base beta is 10, and the exponent in this case is 2. And all of the digits in the mantissa correspond to powers of 10. Because it's the number is normalized, it would always be non-positive powers of 10. So the one digit to the left of the decimal point corresponds to 10 to the 0, and then digits to the right of the decimal point correspond to increasingly negative powers of 10. Now, this is something that we all take for granted, but it's important to keep this in mind to understand how this works in binary. It's all the same as this, just working with a different base. So I want to look at 117 in binary, so now beta is equal to 2. Then this right here is the binary scientific notation version of 117, that the exponent is 6. And the reason for that is if you want to bracket 117 by powers of 2, 117 falls between 2 to the 6, or 64, and 2 to the 7, or 128. So the lower bound here, in terms of magnitude, indicates the exponent. So the exponent would be 6. And then this mantissa here consists of all the significant digits of 117 in binary. So what we have here is a combination of non-positive powers of 2. So the first digit to the right would be, I guess we'd call a binary point in this case, corresponds to 1 over 2 to the first. Second digit is 1 over 2 squared. So these digits are multiplied by 1/2, 1/4, 1/8, 1/16, and so on. And so the number that this represents, which would be equal to the sum of these negative powers of 2, is the original number, 117, divided by 2 to the exponent, 117 over 64.
Professor,
Yes?
why is the exponent 6 expressed in decimal? Well, I think it should also be expressed in binary, like 110.
Oh, in internal storage, it certainly will be.
Okay.
Yeah, I'm just, this is for the sake of a presentation. Students have a hard enough time digesting just from this being in binary. So,
Okay.
yeah, I get your point, but yeah.
Yes.
When we get to storage a little later, it will be. Okay. Well, in that case, I could probably do the same with this, and call it, and then someone's going to think it's 10 to the 110th power. Okay. There are questions about this being 117 in binary. I can give you a general procedure. Like if you have a number, whatever number you choose, and you would like to represent it in binary, like I can figure out what the exponent is and what are the significant digits in binary for the mantissa. Here's how you do it. So to get the exponent, in whatever base you're working in, you take the absolute value of your number, and you take the logarithm in that base. But then you round it down. You take the floor. So recall this notation means floor. So you're taking the greatest integer that is less than or equal to this value. And that gives you the exponent. So if I took the log to base 2 of 117, then I would get 6 point something, and I round it down to 6. That's how you get the exponent. Then you divide the absolute value of your number by your base raised to that exponent, and that gives you the value of the mantissa. Now, the mantissa has not been expressed in any particular base yet. You can probably read it in decimal. but at least the actual value of a mantissa, number represented in whatever base, is given by this formula here. So this guarantees that the mantissa is strictly less than the base. So then there would only be one digit to the left of the decimal point or binary point or whatever you want to call it. So then, how do you express the mantissa in whatever base you want? So you can have at most one digit to the left of the point. So you think of the integer part, so that would give you a first digit in your base. And it's already the correct base because the mantissa is already known to be less than the base. So that's why we needed to do this division. Now, how do you get the next digit? You subtract off the digit you have, and then take what's left and multiply by the base, and now take the next digit and move it to the left of a point. So you can figure out what that digit is. And you keep repeating this process, and that will give you more digits in that base. So now I'm going to show you an example. It's actually from a book, but I'll walk you through it. Okay. So the number I chose for the example is one of my favorite numbers, the natural logarithm e. And e is such a useful number, but pi has pi day. There is no e day, unfortunately. I was hoping that we could observe at least February 7th of 2018, but I could not get any buy-in on that. Okay, so what we do is, as I described earlier. Okay. All right. So first, we take the log to base 2, which is approximately this, and then we round it down, so it's 1. So the exponent is just 1 in this case, which makes sense since e is between 2 and 4. So then we divide by 2. So this, at least the 5 decimal places that are shown here, is the value of the mantissa. Okay, so now I need to represent this number in binary. Now, to the left of the decimal point, we have a 1. So the first digit in the mantissa will be 1. So then we subtract that off, and now we focus on what's left. And I continue carrying out these steps. So whatever you have, you multiply by the base. And what you have here is, you have 0 to the left of your binary point. So the next digit will be 0. Then multiply by 2 again. Now we have a 1 to the left of a point. So the next digit will be 1. When you get a non-zero digit, you subtract it off. And then this process continues. You keep, so you multiply, take the digit, subtract it off. Multiply, take the digit, which in some cases is 0, and subtract it off. And that will give you the sequence of digits. And you can keep going to whatever precision is available, because you only have a limited number of digits that you have. So in this case, I stopped at 20 digits in binary. And these are the non-zero digits that I had. So notice, if you look at the denominators, I don't have all of them. I have 2, 0, and then 2, 4, 5, 7, 8, because of the digits up here that were 0, corresponding to 1 over 2 the first, or third, or sixth. And adding all these together gives the value of my representation, my binary representation, is this. So, so my representation of this number, which is e rounded to 4 decimal places, is fairly close. It's not exact. Even though we have 20 digits of precision, we can't represent this number exactly. but we do have a pretty small error on the order of 10 to the minus 8. So the only numbers that can be represented exactly in binary with a finite number of digits is any number that could be written as a sum of fractions of this form, where you have powers of 2 in a denominator. So, so just as 1/3 cannot be represented exactly in decimal using a finite number of digits, a number that can be represented exactly in decimal, 0.1, cannot be represented exactly in binary. Questions about how this example proceeded? Actually, the way I thought through the example was, again, by dealing with numbers that we all take for granted, working decimal. Like if I had a number written in decimal, how do I extract the individual digits of decimal representation one by one? You're multiplying them by the base to push the digit to the left of the decimal point. Then you subtract it off and work on the rest of the number. You can keep multiplying by the base. So I've shown it here in binary. We instinctively do it in decimal, but the idea applies in any base. So for a general floating point number system, here's how the number is represented. So we have our base raised to the exponent, times plus or minus, and then here are the significant digits. So we have one digit to the left of the point, and then all the other digits that correspond to negative powers of a base. And the total number of significant digits is p, numbered from 0 to p minus 1. The indexing corresponds to the powers of a base that are in the denominator. So d0 is divided by the base to the 0 power, 1. And all these are divided by base to the minus 1, or divided by base to the first, base to the second, and so on. So the total number of digits you have, p, that is called the precision. So it's how many digits you're able to hold in meticulous. So in a floating point number system, p is a fixed value. So based on storage considerations. So you're only allowed to use at most p significant digits in your number. Anything else is lost. That's how some error is incurred. You're also limited for the exponent. The exponent must fall within some range between prescribed limits, L, lower bound L and upper bound U. So once you figure out these four numbers, the base beta, the precision P, and then the bounds in the exponent, L and U, those are the defining characteristics of a floating point number system, because from these values, you can figure out the possible magnitudes of numbers represented in the system, and also how accurately numbers can be represented because of the limits on precision. So what we're accustomed to is, of course, base 10, and then on paper, these values being infinite. But soon I'll get to floating point number systems typically used on computers and what values will be in those cases. Certainly beta is too, but I'll talk about the other values soon enough. So here's some issues to be aware of because of the limited storage available for mantises and exponents. First is about the magnitude, underflow and overflow. So you have a situation where the number is too small to be represented. So, like for instance, let's suppose you are limited to, let's say, 10 decimal digits, and then the lowest exponent possible is, say, minus 20. So You can represent, for instance, 10 to the minus 20, no problem. But you cannot represent the number 10 to the minus 100 in a system like that. You don't have enough digits. And your range of exponents is too narrow for that. So a number that small would be considered 0. So that's an example of underflow. And underflow isn't really a big problem, because if a number is too small to be represented based on the parameters that you have here, you can declare it to be 0, and that's perfectly reasonable. It's a good approximation of a number you can't represent. But it's important to know how small is too small in whatever system you're using. The opposite situation is a big problem. Overflow. So if your range of exponents is, say, for example, minus 20 to 20 in base 10, then a number like 10 to the 100 cannot be represented. So you can think of it as infinity as far as the floating point number system is concerned. And in fact, as an example, I'll go into MATLAB here. Okay, so if I pick a number, say 10 to the 1,000 should do it. It'll actually call it infinity. So there's actually a way of storing numbers where it's understood by the runtime system that is infinite. So really, this number cannot be represented in any sensible way. Another example, if I do 1 over 0, that will also be labeled as infinity. If I do minus 1 over 0, we do have minus infinity. And then finally, what about 0 over 0? So mathematically, what do we consider 0 over 0 to be?
Not defined.
Yeah, not defined. A term for it that's often used in calculus classes.
Indeterminate?
Sorry, what?
Indeterminate?
Yes, an indeterminate form. Because with something like 1 over 0, if you think of it as like a limit, as the denominator goes to 0, then you get the limit would be positive infinity. But we don't have that here. We have no idea what this could be. It just depends. So that's accounted for in the floating point system. NaN, which is short for not a number. So a floating point system accounts for numbers that are too large to be represented. That's a case of overflow. And if it's something you just can't make sense of, then the runtime system has a way to store numbers that's interpreted as an indeterminate form. So when you get this as a result in whatever you're doing, and you know you're really messed up.
Because how does MATLAB store infinity and not that number? You're also using floating points.
I'll come to that pretty soon.
Okay.
All right.
So we will call negative infinity also called overflow, right?
Yes. Yeah. So we can actually know how large is too large. What is the overflow level? So that's called OFL, overflow level. So this is a value for whatever floating point system you have, because this value right here is the largest mantissa you can have. And then you multiply that by your base raised to the highest allowed exponent. And here I've just rewrote the same expression, but this is easier to understand where it comes from. So like in decimal, the largest possible mantissa would be 9.99992, however many digits I would have, a total of p digits. And then I multiply that by 10 to the largest allowed exponent. Now, in the IEEE floating double precision, should make that clear, double precision floating point system, here are the parameters related to that we need to know about overflow and underflow. So this is the largest allowed positive exponent, and then here are how many digits you can have. So you can substitute these values into here, or here, and figure out what the overflow level would be. So in fact, let's see. So I have to be careful how I do this, though. All right. Well, actually, I'm going to do it both ways. So I'll let U equal 1023, and then P is 53. And then my base is 2. So my overflow level, I try to compute it this way. Base raised to the U plus 1 times 1 minus base raised to the minus P. Well, it doesn't like that, which makes sense because it's not allowed to compute this. That's too large an exponent. But if I use the other way, which I wrote it, there. So now we have a value, so it's the order of 10 to the 308th power. So that is the largest number. Now, that actually has a command that lets you know this value called real max, and it is the same value. So you can't deal with numbers larger than that in magnitude. So, questions about overflow?
Single precision is
Single precision,
27.
so what happens is, in double precision you have 64 bits total.
Yes.
So one sign bit, 53, or actually 52 bits are for the mantissa, and that leaves 11 bits for the exponent. And I believe it's 8 bits for the exponent in single precision, and therefore 23 digits. So 24 is the precision in single precision. Okay, actually go ahead and write that down here. All right, so U is equal to, so there's, okay, so we have 11 bits for the exponent, so 2 to that, minus 1. Okay, so there's 8 digits, so 127. Okay, so those are parameters for the single precision. Okay. What about underflow? Underflow is, it depends. So in overflow, you have the largest possible mantissa times the base to the largest exponent. Similar idea here. We have base to the smallest allowed exponent times the smallest allowed mantissa. But what is the smallest allowed mantissa? It depends on whether the numbers are normalized. What do I mean by normalizing? So if you require that the leading digit, the one to the left of the point, is non-zero, then the number is normalized. So here's an example. This is a number in decimal that is normalized. Here's the same number, not normalized. And sure enough, we have a 0 to the left of the decimal point. So normalization is commonly used because it ensures a unique representation of each number. And in binary, what's particularly nice is your digits can only be 0 or 1. And if you rule out 0, then you know that D0 in binary must be 1. Because in decimal, we know that D0, if normalized, must be between 1 and 9. But in binary, 1's the only choice, so don't store it. So in double precision, you have 52 bits set aside for the mantissa. But P is 53. Why? Because there's the implied 1 that does not need to be stored. So normalizing in binary has the extra advantage. I'll write that down here. You get an extra digit of precision. But because the smallest allowed mantissa is now equal to 1, then it limits how small the numbers are that you can represent. Because it's technically possible to represent smaller numbers, but if you require normalization, then you can't do it. So if you are normalizing, then this is the underflow level. But if you are not normalizing, then you can have a smaller exponent because you're allowed to have a mantissa, like in decimal, something like this. Like a bunch of zeros and then a 1 in the very last position. So if I want to get to underflow level, I can use real min, the MATLAB command, to get the value. Now, I could do this. So 2 to the minus, okay. So L is minus 1022, minus 3, minus 1074. Oh, that's interesting.
Oh, smaller than real min.
Okay. The command real min assumes normalization. But I can go smaller because what is done here is, in IEEE, is gradual underflow. So if the exponent is equal to the lower limit, normalization is not carried out. And that's what allows this. So it's interesting that real min doesn't take it into account. Now, if I try to go one step further, 2 to minus 1075, that is too small. It cannot represent a number that small, so it's declared to be 0. Another advantage to not normalizing is you have a sensible way to represent 0. Because if you are insisting on normalizing all the time, your smallest mantissa is 1. That means you have no way of representing 0. But so if I do format hex, I've shown you this one before. If I want to represent 0 in hex, it's exactly what it should be, intuitively. It's all zeros. Whereas if I do like 2 to the minus 1074, the smallest number I can possibly get, that means that the sign bit is 0. That's for the positive number. We have a 1 in the smallest significant digit possible. That's 2 to the minus 52. And then there's nothing in the exponent either. All right. Actually, I'll take a break at this point. Okay. Now, what I've been talking about with regard to underflow and overflow is mainly about the exponents. Not entirely, because the precision does play a role, but it's mainly the rate of exponents that determines what numbers are too large or too small to be represented. Rounding is much more about the precision and how limited it is. Because if you have a real number, such as like any irrational number, that you cannot represent exactly, you are going to incur some error when you try to represent it as closely as possible in the floating point number system. So what error is incurred? It depends on the convention involved. For example, if you have the expansion of a number, like if you could represent it using infinitely many digits in whatever base, like however many digits of pi as you want, Then chopping is when you simply round down. So you simply truncate the expansion after a certain number of digits. So p digits is what is available to you. But that is, of course, not as accurate as rounding, where you round to the nearest number that has a number of digits that can be represented. But what if there's a tie between which number you can choose? How do you know whether to round up or round down? And I remember what I was taught in elementary school was if we have a number like, for instance, 89.5, we're supposed to round to the nearest integer. It could be 89 or 90. We were taught to round up, in that case, to 90. But a convention that is normally used, for instance, in the IEEE system, is round to even. So if you can round in two different directions and incur the same amount of error, you break the tie by ensuring that the last digit is even. And the goal here is to reduce bias in rounding. So sometimes it's rounded up, sometimes it's rounded down. So as an example, so 89.5 is rounded to 90, so you get an A, while 88.5 is rounded down to 88. Okay.
So rounded to odd will cause bias. What kinds of bias?
Yeah. So if the idea is that ties are always broken by rounding up, then so the problem with that is that you're having numbers that are generally larger than your it makes the error like if you think in terms of approximation minus exact, then the error is always positive in those cases. When ideally we like the average on error, the error on average to be 0, sometimes positive, sometimes negative. So by sometimes rounding up and sometimes rounding down,
Okay.
yeah, the expected value of the error would then be 0.
So it will be the same if you round to odd, right? Round to odd.
Oh, yes, that is another acceptable practice.
Yes. Okay.
Yeah. Okay.
Just convention.
Okay. So, a very important concept of the floating point number system is the notion of machine precision. That's one term for it. Another term is unit roundoff, and it's often denoted in numerical analysis text by the bold letter U. So, if x is the number you want to represent, and FL of x is the float of x, is the number that you actually get in the floating point number system, so a number that can be represented, then the relative error so the largest relative error that you can have is one definition of a unit roundoff. And the value of u depends on whether you round or chop. So if you chop, then machine precision is just the value of the least significant digit in the mantissa. So beta to the 1 minus p power. So like 2 to the minus 52 in IEEE. But if you round, that error is cut in half. So this is the value of unit roundoff in IEEE double precision. So roughly 10 to the minus 16. So that is the smallest relative error you can reasonably expect from whatever computations you perform, just because anything smaller than that, less than the error value you would get just from representation of a number. Another definition is not mathematically equivalent to what I just gave you. Is the smallest number you can add to 1 that can be represented by a number greater than 1. So in the IEEE system, that would be 2 to the minus 52. Because, so for example, if I do the following, 1 plus 2 to the minus 53. Oh, whoops. It declares it to be exactly 1. So these numbers are considered equal in the floating point number system because what I'm adding on is considered too small relative to 1. So I can have smaller numbers in this, but if I add them to 1, it can't distinguish from 1. Whereas if I do 1 plus 2 to the minus 52, it's not exactly 1. So there's something added on to it. Now if I look at format hex again, so 1 has this representation. Now this is difficult to decipher, so I'm going to break it down for you. These are hexadecimal digits. I'm going to write it out in binary. And fortunately, hex is relatively easy to map to binary because each one of these hexadecimal digits is equivalent to 4 binary digits. So I would do like 0, 0, 0, 1, 1, and then 1, 1, 1, 1, and then 1, 1, 1, 1. And then everything else is 0 from that point on. Okay. The first binary digit is a sign bit, 0 for positive, 1 for negative. The next 11 digits represent the exponent. And what we have here are 10 ones. So the exponent, the number stored in the exponent is okay, so that's 1, 1, 1, 1. Okay, so that would be 2 to the 10 minus 1. So that would be equal to 1023. Now, to get the exponent, you work out this, you get this number, and then you subtract 1023. So the actual exponent is 0. All the rest of the digits, all these 0 here, that's the mantissa. But remember, we are normalizing. So there's an implied 1. So mantissa in binary is 1 point, all these zeros, 52 zeros. So the mantissa is 1, the exponent is 0, so the number represented is 1. That's how you decipher what you see here. Now, if I do 1 plus 2 to the minus 52, it's almost the same, but we have this 1 here. So there's a 1 in the space corresponding to 2 to the minus 52. Oh, you asked a question about how to represent something like, oh, is it int for not a number?
Yes.
Okay.
Also using floating point.
Yeah, so if I do 1 over 0, let's see what that looks like. Okay. So what we have here is, in binary, that would be 0, 1, 1, 1. Okay. So for the exponent, we have 11 of these 1s. So that's 2 to the 11th minus 1. And you subtract 1023. Well, 2 to the 11th is 2048. So 1024. The largest allowed exponent in IEEE is 1023. So when a larger exponent is represented, that's indicating not an actual number, but it means the numbers can be interpreted differently. So So this is the representation of plus infinity. Whereas if I do minus 1 over 0, I have 1, 1, 1, 1, so the sign bit is 1. So that's minus infinity. And if I do 0 over 0 for not a number, let's see what that looks like. So now we have 1, 1, 1. Okay, so I have 1, 1, 1. 1, 1, 1, 0. Oh, no, that's not true. 8 would be 1, 0, 0, 0. So that's a very odd exponent indeed. Okay. That number would be a pain to work out, but yeah,
It should be some number.
yeah, that's kind of strange. Okay, so that would be
The position.
okay, so we have 1024 plus 12. So all these 8 digits. 1, 2, 3, 4, 5, 6. Okay. That's interesting. So I worked out that number. Oh, that doesn't help. 2040
Yes.
minus 1023. The next one, 1017. If I do minus 2 to the 1017, all right, so here's what I had before. Oh, I goofed.
Yes, they use the same.
Oh, I see why. Oh, okay. I goofed. All right, so I have 1, and then exponent is, and then this is the first part of the mantissa. So it'll be 1 and all these zeros. Oh wait, no. Yes. Yes, it would be. Okay. So this is a mantissa. Okay. Oh. Yeah, I'm supposed to have, yeah, I moved over here. It's all of these digits are equal to 1. That would be 2 to the 11th minus 1. So that's 2047. Okay, so that's still 1024 for the exponent, which is not allowed. So if I compare 1 over 0 versus 0 over 0, actually, okay, these two are almost exactly the same, except for a 1 as the leading stored digit in the mantissa. Both of these have an exponent of 1024, which is not allowed. So, so special cases like int and the n are represented using exponent coding of 1024, which is greater than u.
Yes.
So that way, there's no way of mixing actual numbers with these special numbers. So I made a mistake earlier in how I translated it.
So why do IEEE store such numbers in double position? Why can't they just use another type such that other types not precision double position, but they can free three spaces to store another 3 real numbers, right?
True. You can slightly expand the magnitude.
Yes.
Possible. I don't know like the reasoning behind doing it that way. It's probably an efficiency thing.
Because I'm not sure whether other programming language has also infinity and not a number, these three kinds of variables.
Well, the thing is, this is independent of programming language.
Okay.
This isn't MATLAB. It has some valid displays in text, but this is hardware. So all programming languages dealing with floating point arithmetic are using this system.
Oh, okay.
Okay. So in the IEEE system, okay, this is actually the last thing I need to cover today. So we have 64 bits available, 8 bytes for a double precision number. So those have to be divided between all the components. So 1 bit is from a sine, 11 for the exponent, and then 52 for a mantissa. The first digit under normalization would be a 1. So that does not need to be stored, and that's why our precision is 53, even though there's only 52 bits stored. And that's what I mentioned here, that usually we normalize, so that's why we have an applied 1 for mantissa. And this is what I was describing earlier, yeah, that you have 11 bits for the exponent, you can represent 248 possible values. So you would think that this is a range of exponents, but they reserve these for other numbers or special cases like int and NaN. So that's why this is the range of exponents for double precision. And then here's what it is, I mentioned this earlier for single precision. Single precision, you have 4 bytes total, so 32 bits available. So you have a sine bit, you have 23 bits for mantissa, and then 8 bits for the exponent, which allows this range. Actually, I want to make sure I typed it out earlier. Oh, yes, I did. Okay. These are the same. Okay, so these are parameters of the system that we're all working on, and that computers generally run on, is a double precision. Okay. So as far as format text in MATLAB represents the internal representation. And just to summarize what I showed in MATLAB, 1 hex digit is 4 binary digits. And then the first binary digit is a sine bit. Then the next 11 binary digits gives you the exponent, but you have to subtract 1023 to get it. And then, all other binary digits is for mantissa. With an implied 1. Okay. So that's what's going on with format hex. And I believe I have at least some examples in the text of in case you're interested in seeing how certain numbers are represented. Okay. Like for example, if I take a power of 2, like 1 over 64, then there's no mantissa here because 1 over 64, that's 2 to the minus 6. So the number can be represented entirely using the exponent. So the exponent bits are, so translating the 3 into binary, that would be 0, 1, 1, and then F is 1, 1, 1, 1. F is the hex digit for 15. 8 plus 4 plus 2 plus 1. So I have the F in hex is a 111 binary. And then 9 would be 8 plus 1. So that is the exponent. So then you would work out what number this is by converting this to decimal. So this is 2 to the 0, 2 to the first, 2 cubed, 2 squared, 2 cubed, and so forth. So this would be, this is like 2 to the 10th. So I'd have 1024 plus 512. I have all these ones here, so I keep decreasing. 1, 2, 3, 4, 5, 6. 7 plus 16. Oh, wait. Oh, sorry, I started. Okay, so if I work out what this number is, or have MATLAB do it for me. Dang it, I keep forgetting that. 1017. But I have to subtract 1023. So the exponent is minus 6, which makes sense because 1 over 64 is 2 to the minus 6. Whereas if I have 1 over 64 plus 1 over 128, it's almost the same. So I have 0 for a sign bit, and then 1. And then I have this 8 here. So mantissa starts out with a 1. And then there's zeros after that. So the exponent, that part is the same as the last example. So the exponent equals minus 6. So what we have is, so mantissa is equal to 1.1 in binary, which is equal to 1 plus 1/2, because this corresponds to the 2 to the minus first place. So if I take 1.5 times 1 over 64, and that's the number that I put together. So, okay. All right, just want to do another example of text. So I've been playing around in here a lot, answering questions, but now, actually, I don't have any homework problems on the format hex. It's the way to try to give you a peek under the hood as to how numbers are represented. This is like for your understanding. Okay. Questions on anything homework related? Or it's homework 1, homework 2, quiz. I know I've had a lot of assignments pile up. I actually want to take a look here. With my Canvas dashboard. I have, okay. So 13 quizzes and 12 homeworks, homework 1s, and then let's see, we have one person turning homework 2. Ready to get ahead of the game. Hopefully I can grade those soon, but there's also 23 people enrolled in the class. So we have a number of assignments not turned in. And yes, I have made it clear that I give leeway on those. I just don't want people falling too far behind since we're still not very far in. So let's see if we can certainly get this number up. Okay, well, stick around in case anyone has any questions anyway, but, okay. So, more floating point stuff on Tuesday. what can go wrong with it.
Professor, actually, they have gaps. It is not complete. Real numbers.
Right.
Yes. So always we can find max number. They have orders. Because in real number systems, we cannot find maximum real number, right?
Yeah.
But in the computer system, we can.
Yeah.
We can find max number. What the max number is.
Right. Yeah. If I'm
Just adding
Going
one
to
to
the next
the decimal
Yep.
expression.
Yep.
But then the decimal expression may be the best expression to express because there's no any truncation. Because that is exact how the machine store the number.
right. Yes.
Yes, actually it's 16 digits. Yeah, 16 digits. So times 4.
Yes. Yeah. But that's the full 8 bytes.
Yes.
Yeah. So that's all you have.
Yes. So okay. Oh, thank you, Professor.
Yep.
For the home, instead of summing homework 1, right?
Oh.